warning on the top that the session is being recorded. So now we can start our seminar today. I want to thank everybody for coming, and today it's a pleasure to have Lea from the Institute of Interdisciplinary Mountain Research from Austria and Vivien from University of Heidelberg in Germany about this recent publication that came out in the Earth Surface Dynamics, and it's a very multidisciplinary work on the Äußeres Hochebenkar Rock Glacier. I think we can now start the presentation, and the room is for you. I remind you we have 15 to 20 minutes of presentation and around 5 to 10 minutes of discussion for the public. So the room is yours, and thanks again for presenting your work.
Yeah, thank you for giving us the opportunity to talk about our beautiful rock glacier, Äußeres Hochebenkar in Western Austria. And as the title says, we're basically showing some observational data sets that we have from the site and talking about destabilization that we see in this observational data. And I'll be doing kind of the more general part and giving a bit of an introduction. And then Vivien will take over. We're kind of going to switch back and forth a bit. And Vivien will talk about her methods that she's developing for change detection based on very high resolution point clouds. And she is working mostly at the Rock Glacier terminus. Okay, we can move the slide. We have a picture of the Rock Glacier. Is something moving? Yes, here we go. So there in the center of the picture, that is Äußeres Hochebenkar, or Outer Hochebenkar. We see on the right, there's another rock glacier in Inner Hochebenkar. In the regional inventories for this area, the one in Inner Hochebenkar is usually considered more or less inactive, whereas Outer Hochebenkar is very much active. Also maybe interesting, in that picture we see there is an access road just below the rock glacier snout. So this is a hiking trail and for access to Alpine Club huts further up the valley. And that road has been affected quite a bit by rockfall from the Rock Glacier terminus in recent years. So we have a little bit of this hazard context there too. Hochebenkar has a pretty long history of study, probably because it's fairly easy to access and also quite visible, I guess. And the first records of surface velocity measurements are from the 1930s, and then regular measurements kind of started around the 1950s. Looking at the terrain, the debris input comes from that big rock face there on the right. And another thing worth mentioning in this context of destabilization is that the lower part is quite a bit steeper than the upper part, so the rock glacier kind of creeps over a bit of a terrain step. And as I said, there's a lot of previous literature on the site, and I just want to mention two papers, older papers, one from Hartl and Patzelt from 1982, I think, and another one from Schneider and Schneider in 2001, because both of those papers talk about kind of the rock glacier behavior in a more general sense, and they describe, without using the word destabilization, they describe destabilization processes at the terminus, and they kind of use language like healthy and normal for the upper part of the rock glacier, and they associate this with normal permafrost creep, and then they talk about extraordinary or unusual behavior in the lower section, and speculating about the causes, they figure that this is probably due to a sliding on shear horizons or maybe the bedrock. So they really describe the things that we now see in much more recent literature about rock glacier destabilization. The group where I work currently maintains this time series of surface displacement, which means we go every year and measure the position of marked blocks on the rock glacier surface. This is not part of any particular project. We just kind of do this as part of our long-term monitoring activities. If we can get the next slide. Yeah, that's what this time series looks like. These are mean profile velocities for 4 cross profiles that we have on the Rock Glacier. And we see it starts kind of in the 1950s. There was a period of higher velocities, then it slows down. And then the point I'm trying to make here is that the most recent years, so the last 4 or 5 years, have been really pretty interesting at the lowest 2 profiles. And as I said, we don't have a bigger project around this. We just go and see how the Rock Glacier is doing every year. And obviously, we noticed that something is happening, and we were curious to see if we can kind of figure out in a bit more detail what is happening. So the first step there was to kind of collect some more data. Can we get the next slide? And this is what we came up with. This is not comprehensive. There is even more data that was sort of beyond the scope of what we were able to include, considering no one actually has a project for this. But we found a total of 14 digital surface models, early ones from aerial imagery. Yeah, if you can just click through the slides, Vivien, thank you. So early surface models from aerial imagery, then more recently airborne and UV-borne laser scanning, then those high-resolution point clouds that Vivien is working on, and some orthophotos also from the UV surveys. And there is more detail on all of this in the publication we mentioned. I think what we're trying to say is that we really feel like combining all of this data gave us a much more comprehensive overview of what's happening. And I'm going to hand over to Vivien now for a closer look at this part.
Yeah, thanks, Lea, for the intro. And yeah, it was really great doing this joint research on the Rock Glacier. As Lea already mentioned, in our group in Heidelberg, we are more focusing on the development of computational methods for the analysis of point clouds in general, and specifically for the Rock Glacier, we develop different methods to analyze the 3D topographic change that takes place there. And actually quantifying the change there is quite a challenging task, as yeah, we have a highly variable and also rough surface morphology on the surface of the Rock Glacier, as well as yeah, there are various processes acting and causing the surface to change. And also these processes all act at different directions, at different magnitudes, and also timescales. And finally, since different surface change processes overlap also spatially and temporally, we usually have the signal of multiple processes reflected in the changes that we derive, for example, if we monitor the Rock Glacier annually or even at lower frequencies. So our motivation was to apply higher frequent monitoring in order to also develop suitable analysis methods and to make this step towards the separation of different processes acting at the Rock Glacier. And I'm just now focusing on one study that we conducted recently. So in 2019, we were monitoring the Rock Glacier front that is marked here in this black box at an interval of 2 weeks. So over a full time span of 10 weeks in summer under snow-free conditions. And we developed a new method that was designed to also quantify quite small change in the range of a few centimeters with a high confidence, because methods that we usually have for 3D change analysis are often challenged when the magnitude of change is quite small in relation to the roughness of the surface. And often then we are not really able to derive significant change because the uncertainty that is somehow related to the derived change is higher than the actual magnitude. So the method that we then developed was specifically designed to overcome this issue and basically quantifies change between two timestamps based on corresponding planar boulder faces that we find on the rock glacier surface. So on the right of the figure, you see on the top 2 point clouds of 2 timestamps in light and in dark gray colors. And then the method basically first extracts planar surfaces on, like you can see here in blue and in orange, in the 2 timestamps. And in the next steps tries to find corresponding planes based on their similarity, and then quantifies the change, the 3D change between these planes. And also gives a measure of uncertainty that is related to that change. And with that methods, we were actually able to, compared to the baseline method that we developed this method on, to reduce this uncertainty, or also often called level of detection, by a factor of almost 7. So for the baseline method, we usually had a level of detection of 9 centimeters, and with the new method, we could decrease it to around 1 centimeter. And of course, this is not super relevant if we monitor maybe annually, because then our magnitudes of change are anyways higher than the uncertainty. But especially for such high frequent monitoring, where we really have changes in the order of a few centimeters, this method is quite helpful to still enable the extraction of change in large parts of the area. So we compared it also to the baseline method, and in this lower front area of the rock glacier, we could still derive significant change in around 70% of the area that we investigated, whereas the baseline method was only able to do so in around 16% of the area. And now I would like to hand over to Leah again to take a look at the results.
Okay, I get to talk about the cool animation. These are, does it move for you? Yeah, okay. So these are just hill shades of the 14 digital surface models that we looked at in our paper. And I think everyone who was involved in that spent quite a bit of time kind of staring at it. And the longer you look at it, the more you see. I just want to talk in a kind of really general sense about the lowest part, where the most obvious changes, I guess, are happening. And it's hard to tell just from the animation, but this starts in, so the earliest one is from 1953, and then there are 2 from the 70s, 1 or 2 from the 90s, and then the temporal resolution increases in the 2000s. But we do see kind of 2 separate cycles of destabilization in this imagery. And we use, a lot of what we talk about in the paper is based on work by Marco and Alessandro, who kind of define in a bit more detail destabilization phases and talk about morphological signs of destabilization. So these would be cracks and scarps that develop at the surface and are, of course, very visible in this imagery. And we see for both of the destabilization periods that it sort of starts in that area where the terrain steepens, where the rock glacier goes over this somewhat pronounced terrain step. And also in both phases, we see the kind of progressive development of these scarps and other surface features. If we can go to the next slide. Yeah, this is just another example of things we sort of derived from the data we looked at. On the left, we have, again, hill shades of the DSMs in the background with an overlay of velocity vectors produced with image correlation. And what I want to point out there is, well, on the one hand, in the recent years, the lower section has been really fast. And also we can see in these images that the destabilized section is really delineated quite well from the other part. So this is not sort of a gradual increase in velocity towards the lower part, there's sort of a sharp line, which also coincides fairly well with some of those big scarps we saw in the animation before. On the right is again the time series of block profile velocities at the top, so same data as we saw before. The middle panel shows image correlation-based velocity in areas of where those block profiles are, just to kind of compare the values and also see the different temporal resolution. And the lowest panel shows a bulk creep factor. This is from Alessandro's work. And basically there we make some fairly generous assumptions about the internal composition of the rock glacier, and then compute this bulk creep factor. And for a normal stable rock glacier, the value would be relatively constant and around 1, whereas for a destabilized rock glacier, the values are higher. Can we have the next slide? I think we go over to Vivien again. Yeah.
Yeah. So in addition to that, we also, with this higher frequent monitoring, we're able to take a look at potential variations in subseasonal change. And actually what we found was that there are short-term variations, both in the magnitude of the movement of the rock glacier along the flow direction. So we had magnitudes of movement between 12 centimeters and 21 centimeters within the 2-week timestamps. And also we had variations in the surface elevation change, which was predominantly negative in our case. And the magnitudes of change were around or between 19 centimeters and I think 29 centimeters. So that was also quite interesting to see at this short term that there are variations, and it's interesting to also take a look at this in a more detail also in the future now. And I think I will hand over to Leah again now for summarizing the main findings.
Yeah, I think before I really summarize anything, I'll just once again say that we're just kind of skimming over the contents of that paper. And in a way, I think we feel like that paper was a first step. And that first step was collecting a bunch of data. And there is really a lot more that we could do with this and hope to do with it in the future. Okay, can we see the bullet points? Yeah. And now to summarize, we see 2 phases of destabilization in this data. So the longer term data, more than obviously the subseasonal monitoring that Vivien does. And the destabilization phases we see in the data match really well this idea of kind of a cycle of destabilization, which is also described in mostly Marco's work and some of Alessandro's recent papers. So it goes from normal behavior associated with permafrost creep to destabilization, which is more of a sort of a landslide-like movement, and then deceleration, potentially inactivation. And in our case, we then see kind of another onset of this destabilization. The destabilization we're seeing now seems to be affecting a larger area, and things are moving quite a bit faster than what we had in the 1950s and 60s, although of course that data is less complete. As is typical with rock glaciers, we don't really exactly know why it's going faster now. Of course, we assume it has something to do with rising ground and air temperatures, probably more liquid water in the system. But there are, of course, many open questions there. Again, we all kind of had a good time combining these data sets and thinking about what we learn in terms of the big picture overview to understand the processes and drivers in more detail. And I think there's a lot of room for that. we think it's really important to continue this monitoring. Ideally, it would be a bit more targeted and coordinated. Again, no one has really a project for this. And I think for me, there was also a very valuable lesson in all of this about talking to people in the office next door. So this sounds stupid, but none of the 3 groups that were involved in this, I think, fully knew what the others were doing before we wrote this paper together. And I know there are also other groups in Austria who have worked at the site in the past, and I think maybe still do. And moving forward, if we ever find time, of course, we do also want to reach out to them. And I'll hand over to Vivien once more for our dream of what monitoring could look like at the site. So this is very much in the realm of dreams and not reality, but dreams are great. So Vivien.
Yeah, so as Lea said, we really all appreciated the joint research and putting all the data together, and also taking a look at the different kinds of results that we could extract from the data that we had already. And so in our vision or wish for the future, we would like to have a kind of intelligent Earth observation of the rock glacier, but basically this might apply well also for other phenomena, where we just have multi-sensor observations of the site or landscape scene, and then also at high spatial and temporal detail, also including subsurface data, which is usually quite hard to get from rock glaciers, which then at first produces a very large data set of different time series data set. And then this goes into the different methods that are already there for the analysis of changes at the rock glacier. And it's more meant like there's a big toolbox of methods, and they can all be complementary and can be combined to, in the end, extract the relevant change information that helps us to better understand what's going on actually. And using this change information we have from existing data, might also help us to adapt our future acquisitions and also the analysis. So maybe we find areas that are more active that we might have to monitor more frequently, or there are areas that only experience rather small changes that we have to monitor in higher spatial detail in order to derive some change information. And this can, of course, also be complemented by the combination of using the simulated environment and also machine learning. This is where we currently dive into in our group a bit more. So what is the idea behind is basically based on the information or observations that we already have, simulating different scenarios of change and using these simulated data in order to, for example, train algorithms to learn how different changes might be represented in the data, or in order to find out which are suitable parameters to observe or monitor a specific phenomena, and also with the goal to improve the geographic monitoring of the phenomena. So yeah, we are working at the different parts of it, and maybe in the future it can also be brought together. And I think we would conclude with this vision and are also happy for questions and discussions.
Well, thank you very much for the nice presentation. It was nice to see. Just by the way, this is the rock glacier that is visited by the summer school in over. Okay.
Yes, and the UAV DSMs were collected as part of the summer school. Like that was their
some of the laser
exercise.
scanner as well.
Yeah.
I was there in 2017, I think. Yeah. Great. Well, the room is open for questions from the public. Somebody can raise their hand. Cecil, go.
Yeah, thanks a lot for this great presentation. It was very interesting to see everything you did. And you also mentioned that you have data that were not included in the papers or here. So I'm wondering what type of data, additional data do you have? Like, do you have maybe geophysics or more information about the subsurface on this rock glacier or something like this?
yes, so there is also more surface observation data from other groups, I believe, and I think most of that has been published. I don't know if there's recent coverage. Subsurface information, we have a little bit. We would certainly like more. We have some GPR, also from different years. And Vivien's group has some ERT data from the lower part. Vivien, correct me if I'm wrong. But that's basically it. And this is kind of part of where we would like to be much more targeted in our measurements. So yeah, lots of room for improvement there.
Thanks. Do we have another question from the public? Lea, please.
Yeah, I have another question. Thank you again for the nice presentation. I'm wondering about on the slide where you showed, I think, the seasonal short-term velocities. Did you also measure only up until August, or also later, or maybe in October or September?
Yeah, so the reason why we stopped in August was that there was a snowfall event, and then I think up until end of September, the whole rock glacier was covered by snow, which makes it very hard for us to, monitor it with the methods that we applied. Yeah, it would be really interesting to also apply methods that are able to capture the surface beneath the snow, to also have this somehow these information for the different seasons also over winter, as I guess we expect that different things are happening there than in summer.
Thanks.
We have another question from Hanne. I think her microphone is not working, so asking here. I will read the question for you. Is how will you get hourly data? Time-lapse camera, continuous data with fixed GPS or seismic loggers?
Well, in our vision, all of those things. I'm going to start, and then maybe Vivien can say something. So for me, for our group, we are really on the sort of in situ side of things, and we have for a long time wanted to have GPS sensors on the surface that kind of measure continuously or transmit their position continuously. We do not have that since we do not have a funding, but that would be our goal for the in situ side of things. We do have a weather station with full radiation data, so that would be an interesting thing to tie to it. And Vivien probably has ideas for her methods.
Yeah, having hourly data would be really interesting to also see maybe daily variations in the surface change. However, I think that the methods that we currently use would not be suitable to be applied on hourly data, as the changes would be super small, like maybe in the range of a centimeter, maybe even, probably even less. So I guess then we would have to use different methods. Also maybe fixed installed sensors, as Lea said. But yeah, it would be an interesting thing to investigate, but we currently do not have specific ideas how to install that on the site.
Thanks. Do we have another question? Christoph.
Yeah, thank you for your very interesting presentation. Are you able, or did you try to discriminate the impact of atmospheric warming and the topographical factor on the destabilization? Because obviously the topography plays a major role, since it occurred also in the 50s, 70s. But now the climate changed a lot. So do you have an idea how far this the changes in the in the warming of the permafrost impacted the velocities of the rock glacier?
that is kind of the question for me as well. And I'm going to have to repeat what I keep saying. We don't really know, and we would really like to continue work in this direction. So if anyone would like to join forces also for a weave proposal or something like that, we are all ears. Please do reach out. At the moment, we have, of course, kind of speculations and ideas, as I assume all of you would be able to come up with. We can't quantify it. There is some BTS data. Hartl and Patzel did that during their investigations in the 70s and 80s. It was repeated sort of in the 2010s at some point around the Rock Glacier terminus, so in the areas next to the terminus, and temperatures are higher, and we obviously see some degradation of permafrost in the way you would probably expect at this elevation. Saying anything more detailed is going to be really difficult. I think we would need to combine it with meteorological data, which we kind of have, so we're not in a terrible position, I think, to keep thinking in that direction. But as I said, this was a first step, and there are many steps left to take potentially.
Thanks. Do we have another question? Please raise your hand or just write on the chat. But not really. Well, I think that is all the questions from the public. So I want to thank you both again for the nice presentation of this site. It's well done, and yeah, I think you are in the right direction, doing this multidisciplinary work, joining forces together with other institutes to really look on this rock glacier, and yeah. From that, I just want to say that we have a final seminar for this semester. That is, we have a, no, Christoph, can you, no, you raised your hand, but it's stuck. Cecil is going to give us the next seminar, the 31st of May, no? If I'm right. And then, yeah, that will be the last for this semester, and probably I'm just asking for new presenters for the next semester. We have some people already joining, so there's still 1 or 2 places available for next semester if you want to give a talk in the seminar series. So thank you everybody for the questions, the participation, and the two presenters as well. And see you on May.
Thanks, everyone.
Yeah, thanks everyone, and thanks for the invitation.